Officially, this is 47th Flow seminar. My name is Samuel Horvath, and together with Peter Richtarik, Virginia Smith, Aurelien Bellet, and Dan Alistair, we are the organizer of Flow seminar. For those of you who are attending for the first time, Flow seminar stands for Federated Learning One World Seminar, and it was created as a global online forum for the dissemination of latest scientific research in all aspects of federated learning, including both theory and applications, and areas such as distributed optimization, learning algorithms, privacy, cryptography, personalization, systems, hardware, and many more. For today's talk, it's my great pleasure to introduce you our speaker, Haoyu Zhao. Haoyu Zhao is a PhD student at Princeton. In his research, he's broadly interested in theoretical computer science and machine learning. Some of his particular interests include deep learning theory, optimization, and federated learning, online algorithms, and online learning. And today he's going to talk about his recent work on a fast local stochastic gradient methods for communication efficient federated learning. So Haoyu, please, stage is yours.
Okay, so hello everyone, I'm Haoyu Zhao, and today I'm gonna talk about FedPage, which is a fast local stochastic gradient methods for communication efficient federated learning. And this is a joint work with Zhize and Peter. So this is a brief overview of today's presentation. So first I will give a brief introduction about federated learning and our framework and show some related works. And then I will define our problem setting and show some assumptions. And in the third part, I will go over our FedPage algorithm in detail. And in the fourth part, I will show the convergence rates of FedPage in different settings. And in the fifth part, I will give a very high-level proof sketch. And then in the final part, I will show you some numerical experiments. Okay, so let's get into the first part, introduction and related works. So in our framework or in our model, we assume that there is one central server and there are n clients. And for simplicity, we assume that each client holds M data. And we assume that the clients can communicate with the central server, but cannot connect with other clients. And note that this may not be true for some federated learning applications, especially those related to the multi-agent problems. So in those problems, there is a communication graph, and the clients can only communicate with the neighbors in the communication graph. But in our settings, we just assume that there is a central server, and all of the devices or all of the clients are connected to the central server. And we assume that there is a global model saved on the server, and the clients communicates with the server to update the model. So below is a federated learning application. So in this application, we want to predict the next words we will type. And there is a global model stored on the central server. And the model may be a neural network or maybe some other machine learning models. There are lots of devices, and in this figure, the devices are just the mobile phones. On each device stores the local data. For example, the sentences already typed in from the mobile phones by the users. And the central server communicates with the clients, and the clients compute some message or information based on the local data. And then the clients send back the messages and the information back to the server. And finally, the server updates the model, and hopefully in the end, the model can successfully predict the next word we want to type in. And an optimization problem. So function of a machine learning model with respect to all of the data across all of the devices. And we just assume that the functions fx of n functions fx, where fx is the loss function of data samples stored on device I. And we further assume that the functions fx is also an average of m functions fijx, where fijx denotes the loss function according to the jth sample stored on device I. And in our framework, at each communication round R, the server first broadcasts the current model XR, or also broadcast some other messages to the client's SR. And the clients compute some functions, GIR, and transfer back to the server. And then the server updates the model according to GIR. And this is the process in one communication run. So there are at least 3 challenges in the federated learning applications. So the first is the expensive communication, and the second is the heterogeneous data, and the third is the privacy. In federated learning applications, the communication is usually the bottleneck, and we want to use as fewer communication bits to train the model as possible. Besides, the data in federated learning applications are usually heterogeneous. That is, the data on different devices may not come from the same distribution. So recall the previous word prediction example. Different devices store different sentences typed by the users. And even if all of the people are typing English, different people may have different habits. For example, some people may use American English and some others may use British English. And we cannot assume that the data on different devices comes from the same distribution. As for the privacy issue, we cannot directly transfer the personal data to the central server or share our personal data with other clients. So in our framework, we do not transfer the data directly to the central server, and we only transfer some message, and this partially solves the privacy issue. And we never assume that the functions fi or the functions fij are similar, and we just view them as arbitrary functions. And this solves the heterogeneity issue or the non-IID issue. And now the remaining problem is the communication problem. That is, how do we deal with the expensive communication? And this is actually the main focus of this paper. And to solve the communication issue, there are at least 2 main lines of work to overcome the communication problem: the algorithms using compression operators and the algorithms using local updates. So for the algorithms using compression operators, the philosophy is to communicate as less as possible during one communication run. And for algorithms with local updates, the philosophy is to let the devices to do more things or do more works or performing multiple local steps during one communication run, hoping to reduce the total number of communication run. So this is a very simple example about the communication operators methods. So there are 2 devices, right? The left and the right. So first, the devices received the global model XR from the central server. And then they compute some message GIR, G1R and G2R. But instead of directly transfer the message back to the central server, it will first compress the message into some compressed version. So for example, it compressed G1R into CG1R. And the compressed message may be either sparse or below precision. And they just use fewer number of bits to represent. And then the device just sends the compressed message back to the central server, and hope that in the end, by using the compressed method, by using the compression operators, the total number of communication bits transferred during the training process is small. So there are already some works related to the compression operators. For example, the QSGD and SunSGD algorithms, which can be viewed as the compressed version of the stochastic gradient descent. And there is also the Diana method, which is the compressed version of SVRG. And there is also A-Diana, which is the accelerated version of Diana. And another line of work is the local method. And this image is a very simple example about the local method. So there are also 2 devices, and each device first receives the global model XR from the central server. But instead of directly compute something and transfer it back to the cloud or to the central server, the device may first perform some local steps and compute some local models. For example, it will first use the message to compute a local model Y11R, and then compute some other message and updates to Y12R. And maybe after K local steps, the model becomes Y1KR. And then the device transfer back the model difference between XR and Y1KR back to the central server. And by doing multiple local updates during one communication run, we hope that the total number of communication run during the training process can be as few as possible. So there's also some works related to the local methods. For example, the Fed average algorithm, which can be viewed as the stochastic gradient descent with local steps, and local SVRG algorithm, which is the SVRG with local steps. And there is also the current state-of-the-art scaffold algorithm, which is the Saga algorithm with local steps. And our Fed page algorithm also belongs to this line of work. And our Fed page algorithm can be viewed as the page algorithms with local steps. And now let's go into the problem settings and assumptions. So we first recall that we formulate our federated learning application as an optimization problem, or more specifically, a finite sum problem. And recall that here, fi, x are the functions stored on device I, and these are the loss functions of data samples on device I. And we further assume that these fi(x) are also finite sum problems, and they are an average of m small functions fijx. And in this project, we consider two different settings, the non-convex setting and the convex setting. So in the non-convex settings, all of the functions can be non-convex, and we want to find a point x such that the expected gradient norm is smaller than some small constant epsilon. And in the convex setting, we assume that the resulting function fx is convex, but we never assume that the small functions fix or the small functions fijx to be convex. And all of the functions except the final functions fx can be non-convex. And in this scenario, we want to find a point x such that the expected gradient, the expected function value difference, fx minus f star, is small than some constant epsilon. Here, f star is the optimal of the convex function f. So in this project, we made two assumptions. The first assumption is the very standard L-smooth assumptions. So in this assumption, we just assume that all of the functions fij are L-smooth. And here I want to mention that we can extend this standard L-smooth functions to support different smoothness constants. For example, we can assume that the functions fij are Lij smooth by using some important sampling technique. But for simplicity, we just assume that all of the functions are L-smooth in this project. And we also made another assumptions, that is the bounded variance assumptions. So basically, this bounded variance assumption says that if we fix a client or fix a device I, then we compute the stochastic gradient on this device I. Then the variance of the stochastic gradient is bounded by some variance epsilon square. And we only use this assumption when the number of data on a single device is very large. For example, we only use this assumption when m is very large. In this case, we may not go over the data for even once. We may not compute the local full gradient. And then we will use this assumption and maybe sample a batch of data to represent the whole data and compute something. So is there any questions?
So it seems there are no questions. So just as a reminder, if you want to ask a question, please either raise your hand or post your question to chat and I'll try to unmute you.
Okay. Then.
Oh, there is one question.
Okay.
I'll try to unmute Gonzalo.
Under which conditions the total function f can be convex? Are there any examples? Currently, I don't think that there's many intuitive examples, but let me think.
Yeah, so maybe if you could like read out loud questions so people don't need to read it again. And then
yeah, so actually the question is, under which conditions the total functions fx can be convex, even though the client functions f(x) are not convex? Could you give an example? I think there may be some cases when I think that there may be some cases when the number of data is very large or the number of clients is very large. So for example, in expectation, the function should be convex, but if you just select one client out or select a data sample out, then this may not be convex. But yeah, I guess this case may, yeah, I guess if this is the case, then there may be the total functions fx may be convex and the client's functions fx may not be convex. Yes, but currently I do not have any very intuitive examples.
Okay, so maybe, yeah, let's continue. It seems there is no other question.
Okay, yeah, let's continue. So now let me go over the fat page algorithm. So okay, maybe another question.
No, that's just okay. Thank you for the answer.
Okay.
So please continue.
Okay, so we already said that our fat page algorithm is built on the original page algorithm. So now let's first review how page behaves in the federated learning setting. So this algorithm is the page algorithm, and all of the blue lines are executed on the central server, and all of the red lines are executed on the client. So the input into the page algorithm is a sequence of probabilities PR. The PR is here, and PR denotes the probability to communicate with all of the clients in round R. So actually in line 4 to line 6, this is the case when the central server wants to communicate with all of the clients. And this case happens with probability PR. And the central server will communicate or broadcast the current global model XR to all of the clients. And then on the client side, every client compute the local full gradients. And then in line 6, the central server just average all of the local full gradients and compute this direction GR. And in another case, that is line 8 to line 10, the central server does not want to communicate with all of the clients. So it will sample a subset of clients with size S and send the current model, the previous model, and the previous direction GR-1 to the clients. And then on the client side, after receiving these informations or receiving these messages from the central server, it will compute this GIR, which is a recursive gradient estimator. So if we just eliminate the last two terms, so now GIR is just the stochastic gradient of client I, right? The local full gradient of client I at the point XR. And the last two terms are used to reduce the variance generated from the client sampling procedure. So yes, we want to reduce the variance. And then after computing this GIR, the function generated from device I in communication round R, and the clients send this back to the server. And then the server just average all of the directions from the selected clients. And in the end, the server perform a global step in the direction GR that is computed in line 10 and line 6 with the step size eta g, where we denote eta g as the local learning rate or the eta g as the global learning rate or the global step size. So yeah, this is the page algorithm in the federated learning setting. So we said that we can use local, okay. Yeah. Do you assume that each, so the question is, do you assume that each client can compute full gradients, not also stochastic gradients? Not also stochastic gradients. Okay. Not only stochastic gradient. Yes. So in this page algorithm, we need to compute the local full gradients. Yes, the full gradient at each client side. But we will see that after I introduce the Fed page algorithm, we do not need to compute the local full gradients, or we only compute the local full gradients when it is affordable. Yes, so I will answer this question in the following presentation.
Okay, thank you.
Okay, that's fine. So we already said that we can add local steps into the page algorithms. So how to do that? So recall that the local steps only happens on the client side. So we only need to modify line 5 or line 9. And because we never want to communicate with all of the clients at a very high probability, so the probability to execute line 5 is a really low probability thing. So for simplicity, we just keep line 5 as the same, and we only add the local steps into line 9. So here is the simple version of the local steps. So this procedure also computes the local full gradient, but we will modify this local steps again. But we can first understand this local steps or how this local steps works. So for example, all of the notations or all of the variables y, I, k, r denotes the local steps or the local models stored on device I. So at first, each device may copy the current global model and then compute a direction. So we can compare this line with the previous page, line 9, and they are exactly the same. So actually here we compute a direction. And then we perform a local steps, right? We perform a local update with the step size eta L, which we denote as the local learning rate or the local step size. And then for the following k-1 steps, right, we recursively update this local direction. So we can see that GIKR is equal to this variable. So here we also compute 2 local full gradients, but in the end we will not computing it. So but here it is easy to understand. And so this is also a recursive update. And this update is also similar to the update in line 3, except that the line 3 uses the global models, but now we update using only the local models. And then we perform several local updates in this for loop. And then in the end, we just transfer the model difference back to the central server. So the intuition of this local steps full is that if we choose the local learning rate to be very small, for example, if we choose eta L to be smaller or even close to 0 or even equals to 0, then all of the local models YIKR are very close to the original global model XR. And then from the smoothness assumptions, right, all of the gradients, for example, these gradients in line 6, the first 2 terms, are also close to each other and they can nearly cancel out. And then all of the local directions, GIKR, are close to the original GI0R, which is close to the direction computed by the original page algorithm. So all of the directions are close to line 9 here. So very similar to the very close to the page computation. And then the final direction, delta YIR, is also very close to the original page direction. So yes, the intuition is that if we choose the local learning rate eta L to be small enough, then everything works like the original page. And we can expect that by using these local steps, the algorithms can converge. So this is how we incorporate these simple local steps into the page algorithm. So compared with the original page algorithm, this algorithm only changes the line 9. So originally we compute GIR, but now we change it to use a local steps full. And then we also change line 10 accordingly, but this is not a very big difference. So now we successfully add the local steps into the page algorithms, but there are two problems, at least two problems. The first problem is that in the fat page full procedure, we compute k local steps or 2k local full gradients or k local full gradients at each client when performing the local steps, which is time consuming. So yes, so in this algorithm in line 6, right, we need to compute 2 local full gradient. So the total number of local gradient is at an order of k, and it is a little bit time consuming. And the second thing is that when M is very large, when the number of data stored on a single device is very large, computing the local full gradient may not be affordable. So we want to optimize the local steps. So yes, so if we have a look at this equation 1, this is just the updates rule in local steps full. So this is the first update. This is exactly same to page. Yes, let's. Oh, sorry.
Okay, so
what is the advantage of page? So the question is, what is the advantage of page algorithms itself when we compare to SVRG or other algorithms? So if you have a look at the original page paper, so we can find that its convergence rate in the non-convex setting is better. So for page algorithm, it reaches square root of n, but for SVRG, it only reaches n to the 2/3, n to the 2/3. Oh, it's Zhizhe saying that I will just keep going.
Okay, thank you.
So if you have a look at this equation 1, it is the update rule from the local steps full. So right, this is the recursive update, and we use the full gradient here. And then we can change it to equation 2 by substituting this yellow part, computing the local full gradient by only using a single number of by only using a single data. That is, here we compute the gradient fi, right? We compute the gradient fi, but now we just randomly sample a data j and compute the gradient fij. Here we only compute the gradient fij. So now, compared with equation 1, except for the first, the local full gradient computations in the first small local steps, we never compute more local steps now. So the number of local steps computed in equation 2 is only 2. And then when M is very large, right, we cannot even, computing these 2 local full gradients may also be unaffordable. So now we use a large batch of data to represent or to estimate the local full gradient. So now we see that we substitute the original local full gradient computation by using a batch of data. And if M is not very large, we just choose this to be the full batch. And when it's large, then this batch has some dependency related to the sigma square. And if we put the previous equations into the locals, into the algorithm, then this becomes the final local steps for Fed page. And the only difference is that we change the line 3 to use a batch of data to estimate the local full gradient computation. And then in line 6, instead of using the local full gradient to update the local directions, to update GIKR, we first sample a data J from the device I, and then update the local directions by using this by using this data only. And this is the local steps of the Fed page algorithm. And then by putting these local steps into the page framework, we get our Fed page algorithm. So compared with the original page algorithm, there are two differences. The first is at line 5. Previously, we need to compute the local full gradient, but now we also use a batch of data to substitute it. And then in line 9, previously we compute the recursive gradient estimator, but now we also use the local steps to substitute the original line 9. And this is the final version of Fed page. And this is the full algorithm of Fed page. Yeah, so is there any questions?
Yes, I would have one quick question.
Okay.
So is your focus here for CrossSilo federated running because that with the small probability you require every single client to participate? Or do you?
Pardon. I didn't.
Oh, so is your focus here CrossSilo federated learning because of your Fed page algorithm requires with small probability to every single client to participate. So in cross device, I don't think this can be kind of a reasonable assumption because you have like millions of clients and only few of them are available at given time. So I'm actually just asking about your focus for Fed page.
Oh.
So is it CrossSilo?
It's CrossSilo. I think, yeah, I think that actually the communication is the bottleneck, right? So yes, so actually, even if all of them are active, so even if you can communicate with, for example, all of the clients, but if this is the case, when the clients transfer some message back to the server, then they will get stuck because the bandwidth is limited. So that's why we choose a small s, a small number of clients to be communicated with. Yeah, that is why each client may only participate into the communication with a low probability, because in total we want to reduce the total number, the total communication complexity. Yes, and actually we will see that we can communicate with all of the clients. For example, we can choose S to be at the order of n, but if that is the case, our communication complexity cannot is just similar to, for example, the gradient descent. And yes, and there is no improvement compared with gradient descent. But if we only communicate with a small number of clients, the total number of complexity, we can see a huge improvement on the total number of complexity, the total communication complexity. Yes.
Yeah. Okay, so we have question from Osman. I'll try to unmute you.
In the same direction. It seems that even PR equals 0, we probably still can converge if the sampling of S is non-biased. Is that true? Yes, I think that is true. So for algorithms like SVRG or loopless SVRG or some other methods, we use some probability to compute the full gradient, right? But there is also some other methods like Saga, right? So for algorithm Saga, except for the first round, it never needs to communicate with all of the clients, or it never computes the full gradient. So yes, I would like to refer you to the algorithm Saga, and that is an example of an algorithm that PR is equal to 0 and can still converge if the sampling of S is not biased.
Okay, I'm sorry. I have another. My question. Okay, there is another detail that I had in the same direction. So in your case, I mean, even the algorithm you presented now can still converges even if we have PR equals 0 for all rounds, right? Because in any cases you will keep track of gradients because you communicate with subsets of the clients at each round. But I don't see what is the advantage of really having this communication step where everyone communicates. I don't see what is the advantage of this step. Okay, it's clear an acceleration, but it's too costly. So I don't know if it's like really necessary in your algorithm or not.
Okay, so to my understanding, this question is asking why the page algorithm or the Fed page algorithm needs to use a very small probability to communicate with all of the clients, right?
Yeah, why not 0? Yes, exactly.
Yes. So I think that I can answer this question intuitively. So the first thing is that in experiments, if you run the original page algorithm without the probability to communicate with all of the clients, then it will diverge. And I think that intuition is that. So let me back to the original page algorithm. So the intuition is that. So now let's just think about the finite sum problem. So here Fix is just a gradient, right? So we never consider the federated learning setting. So we can consider the variance of this GIR. So this is the recursive gradient updates. So if we never communicate with all of the clients, then we will update this line with probability 1. And note that we randomly sample this client's I, right? So actually, if we look at this gradients under the full gradient, that is, if we compare this with nabla FXR, then it will introduce some variance. And if you have a look at this equation, then the variance goes up every step. So if you do not have a probability to communicate with all of the clients, then the variance will go speed up. Yeah.
But, I'm sorry, I don't really agree with that line because it's followed by an aggregation step.
Pardon?
I don't really agree with what you just said because you see at each step I compute the gradients, but then I average them. What you said is true when I don't average gradients, but here at each time I compute the gradients in the way you just said, I average them after that. Okay. So this is an estimation. In reality, what is done here, I mean, this step is an estimation of the full gradient of the sum function. So I don't see why it should like really diverge. For me, it seems to converge. If the sampling is not biased, then this should converge. I don't see why if the sampling is not biased, this will diverge. I don't see why.
So actually, your question is that because we average the functions here, so you think that this, for example, this information is actually behaves like some full gradient information, right? So
yeah, some estimation of full gradients. Yeah, that's what I think.
Yes, but you should notice that we only select a sample, right? Or we only select a subset. So for example, we can just change this size S to size 1. We can just change S to 1. Yeah. And then you are never computing the full gradient. And you may introduce some variance compared with the full gradient. And then the variance sum up. So that is, I think, that is an intuitive explanation. No, but I think that if you change the algorithm, you may not need to communicate with all of the clients. Yes, I partially believe that.
No, just on the last point, if we with example equal 1, if you compare this with the like vanilla stochastic gradient, in which we just sample at each point one data point, and I mean, we are doing almost the same thing. I mean, no, because you update sample by sample, but then you are keeping track of the old gradients, and I don't know. In this case, this will reduce maybe to, I don't know. It's similar to stochastic gradient plus variance reduction. So I don't see why it should converge. I mean, if you have a decay in learning rate, it will converge to the exact solution. But maybe I'm wrong. I don't know. Maybe I'm wrong.
So maybe if you have a look at the stochastic gradient descent, right? So if you just delete the last two terms, then this is just stochastic gradient descent. Therefore, SGD, the variance of this term is the same. So the variance of GIR are all the same. And because you can think that all of them are independent, so the total variance after T steps is something like square root sigma square over T. But now, because you recursively add it up, so for example, G1R or just G1, right? It's G1 is only sigma square, but G2 is 2 sigma square. And then the variance for G3 is 3 sigma square. And then the variance for G4 is 4 sigma square. Yeah. So it blows up. So, but I partially believe that if you change this kind of recursive updates, for example, if you change it to some other formulations, I may think that you can just drop this kind of you can drop the communication to all of the clients. Yes, I partially believe that. But currently for page, for experiments, it does not converge. Yes.
Okay. Okay. Thanks for the clarification. Thank you very much.
Okay. So now let's get into. Oh, there's another question.
That's a comment from.
Oh, okay. So now let's get into the convergence results for fat page. So let me first show you the convergence in the non-convex setting. So under standard assumptions, that is the L-smooth, the standard L-smooth assumptions, and the bounded variance assumptions. If we choose the parameters properly, these parameters includes the probability sequence PR, the global and local learning rates, and the batch sizes. Fat page will find a point X such that the expected gradient norm is smaller than some constant epsilon within the following number of steps, within the following number of communication round. So the number of communication round, if we choose S to be smaller than square root of N, is only square root of N over S times epsilon square. And the number of communication round matches the convergence rate of the original page algorithm. And then for the total communication complexity, is N plus square root of N over epsilon square. And the first term N comes from the fact that we need to communicate with all of the clients in the first round. And we can compare our fat page algorithm with the current state-of-the-art scaffold algorithm in the non-convex setting. So in terms of the communication round, our fat page algorithm improves the communication round by a factor of N to the 1/6 S to the 1/3. And as for the total communication complexity, we also improve the communication complexity by a same factor, N to the 1/6 S to the 1/3. And this is due to the fact that fat page and scaffold communicate with the same number of clients in expectation. And from this comparison, we can conclude that fat page is more suitable when the number of clients N is very large. For example, the federated learning applications related to mobile phones or personal computers. And this is the convergence theorem of fat page in the convex setting. So still under standard assumptions, if we choose the parameters properly, fat page will find a point X such that the expected the expected function value difference is smaller than epsilon within the following number of communication rounds. And if we choose S to be smaller than S square root of N, then the total number of communication round is bounded by N to the 3/4 over S times epsilon. And the total communication complexity is N plus N to the 3/4 over epsilon. And this is also because we communicate with all of the clients in the first round. So compare with the current state-of-the-art scaffold algorithm, we include the communication rounds and the total communication complexity by a factor of n to the 1/4. And now let me briefly give you a very high-level idea about the proofs about the proof idea. So actually, let me first give you the high-level idea in the non-convex setting. So the main part in our derivation is to bound this variance term. That is, we want to bound this term, the term shown in line 1. So actually, if we can bound this term, then everything behaves like gradient descent, right? So or stochastic gradient descent. So the most important thing is to bound this term. And note that when the number of local steps is set to 1, that our Fed page algorithm reduces to the original page algorithm. And so in line 2, the first term is just the direction computed by the page algorithm. So from the page paper, we already know that it is easy to bound the variable in line 2. So compare with line 1 and line 2, we only need to bound the term in line 3, which is the difference between this GR, the direction of Fed page, and this term, the direction computed by the page. And further, we can use some further in line 4, we only need to bound line 4. And then by using something like Cauchy-Schwarz inequality or Young's inequality, we can transfer line 4 into line 3. Because if we unrolling this GR, then it is an average of some, for example, of GIKR for some I and for some K. So if we can bound the terms in line 4, then we can successfully bound line 3. And then it comes our intuition. If the local learning rate eta L is small, then all of the local models are close to the original global model. And then all of the local directions are close to the original direction. So we can bound this. And then the above equation will be small. And then if we can bound this, we can just backtrack to the original variable we want to bound, the variance term we want to bound. And then in this case, we can successfully prove the convergence rate of Fed page in the non-convex setting. And in the convex setting, things is a little bit different. So recall that page and Fed page uses the biased gradient estimator. And unlike the algorithms like scaffold and SVRG, for example, or SGD, they use the unbiased gradient estimator. So if we write out a descent lemma or some, a descent lemma, then we cannot throw away the inner product term. That is the term shown in line 2. So for SVRG or scaffold, for SVRG or scaffold or saga, these gradient estimators are unbiased. So if we take the expectation, the first term will be 0. And we can throw that term away. But for our page and Fed page algorithm, we cannot throw that term away. So we need to use some technique to first bound this inner product term. And after bounding this inner product term, for the proofs of the page algorithm, it behaves similar to, for example, for SGD or for GD or for SVRG. And the next step is to go from the page to the Fed page. So still we need to consider the local error generated from the local steps. That is, it is very similar to the case in the non-convex setting. And we want to still need to bound this kind of local errors. And then we just reuse the previous result from the non-convex settings and bound these local errors. And then if we combine these two ideas together, we can just finish the proof for the non-convex setting. And this is a very, very high-level proof idea. So in the final part, I will try to show you some numerical experiments. So actually, we use two different objectives. The first is the robust linear regression, and the second is the logistic regression with non-convex regularizer. So for robust linear regression, the function is shown in line 2, and it is a non-convex function. And for the logistic regression with non-convex regularizer, so the function is shown in line 3. And the first term is just the loss function for logistic regression, and the first term is convex. And for the second term, it is a regularizer term, and it is non-convex. And the regularizer coefficient alpha is set to 0.1. So we perform 2 experiments. The first shows the effectiveness of the local steps, and the second compares FedPage with other methods. So actually from the previous theorems, we only say that the convergence rate of FedPage matches the convergence rate of page, which means that from theory, we do not see any theoretical improvements by using the local steps. But this does not mean that the local steps are useless. And we actually shows the effectiveness of local steps in this experiment. So in this experiment, we consider 3 algorithms: FedPage 1, FedPage 10, and FedPage 20. So FedPage 1 means FedPage using only 1 local steps, which reduces to the original page algorithm. And FedPage 10 and FedPage 20 means that FedPage using 10 and 20 local steps respectively. And in the leftmost column, each client holds 10 data because yes, we set the number of clients to be a little bit large. And in the middle column, all of the clients holds 100 data. And in the rightmost column, the above page, in the upper page, each client holds about 3,000 number of data. And in the bottom image, each client holds about 5,000 number of data. And we test them on different data sets. And we choose the objective functions to be robust linear regression. So although we change the number of clients and we change the data set, we can find the similar patterns. That is, the FedPage algorithm with the local steps behaves better than the algorithms without the local steps. And we can actually see some gaps in the final convergence. Right? And because this is the non-convex setting and the curves are really flat in the end, so actually this gap is a significant improvement. And the other experiment is the comparison between the FedPage algorithm and the scaffold and FedAverage algorithms. So here we list the blue line represents the FedAverage algorithm, the orange line represents scaffold algorithm, and the green line represents our FedPage algorithm. So for all these 3 algorithms, we choose the number of local steps to be 10. And in the experiments, all of the clients holds 10 number of data, holds 10 data or holds 10 samples. And for FedPage algorithm, we choose the number of clients to communicate with all of, we choose the clients to communicate to be 10. That is, we choose S equals to 10 in the FedPage algorithm. And for FedAverage and scaffold, we choose the S to be 20. And this is because in FedPage algorithm, we may choose to communicate with all of the clients with a small probability. And we just set S to be 20 for scaffold and FedAverage and S equals to 10 for FedPage to make sure that in expectation, these algorithms communicate with the same number of clients or nearly the same number of clients in the same communication run. And recall that there is only 10 samples. So for FedPage, in the first local steps, we directly compute 2 local full gradients, and this cost 20 gradient computations. And for the remaining 9 local steps, we only need to compute 2 gradients at each steps. So in local steps for a single client, our FedPage algorithms compute 38 number of gradients. So we set the number of, we set the mini batch for FedAverage and scaffold when computing their local, directions to be 4. So if we set, if we use a mini batch of 4 for scaffold and FedAverage, then the local steps computes about 40 number of local gradients. And this makes sure that the local computational cost is also nearly the same for these three algorithms. And this is the results for robust linear regression on different data sets. And we can see that actually our fat page algorithms behaves at least as fast as scaffold. And in the first data set, it behaves much better than scaffold. And in the second data set, we think that we may not select the learning rate very carefully. And if we select the learning rate to be larger, then we can still see a gap between our fat page algorithm and the scaffold algorithm. We also test our methods on with different objectives. That is, we test it with the logistic regression, with the non-convex regularizer. And in these experiments, we can see that actually in almost every cases, fat page converges much better than the scaffold algorithm. And actually, in conclusion, we design a fat page algorithm, which is a communication efficient local method for federated learning. And secondly, from theory, we improve the communication runs and the communication complexity of the current state-of-the-art scaffold algorithm. And finally, from the experiments, we also show the effectiveness of the local steps and show the superiority of fat page over other existing methods. And that is the end of my presentation. Thank you very much. So questions are welcome.
Thank you, Haoyu, for your great talk. So please, if you have any questions or comments, now is a good time to post them to the chat or just raise your hand and I'll unmute you. There is a question from Hao. Soon I'll try to unmute.
Do they have similar computation complexity? So the question is, compared with scaffold, do they have similar? So if we compare fat page with scaffold in terms of the computational complexity, is there any difference? So actually from our theorem, so first I need to mention that scaffold and fat page are not very easy to compare with. So if we do not consider the bounded variance setting, so if we can compute the local full gradient, then the computational complexity for fat page is the communication run times m plus k. So when m is not very large, so we can choose k to be some decent number, and m plus k is really acceptable. But for scaffold, scaffold currently does not support to change the mini batch size during the local steps. So actually, it is not very easy to compare with. And in terms of the bounded variance setting, so I think that scaffold behaves similar to the stochastic gradient descent. Yes, scaffold, the total computational complexity for scaffold behaves very similar to the stochastic gradient descent. And our fat page is worse than a very small constant, a very small factor. Yes, it needs to compute a little bit more gradients, but its communication round is much smaller than compared with scaffold. Yes.
Is there any other question? So I would have a quick one. Okay. So in your work, you don't really require any similarity between clients, right? Is that correct?
Yes. Yeah. We do not
but
assume any similarity.
While scaffold requires that, right?
No, scaffold does not require that.
Even for non-convex setting?
Yeah, even for non-convex setting. So actually, So scaffold listed, I think in the paper, scaffold listed some similarity assumptions, right? The similarity gradients and the similarity,
between clients.
hashes.
Like, yeah.
So yeah, but they have two parts. So the first part corresponding to the Fed average algorithm. So they first prove another bound for Fed average, and they use that assumptions in that part. And then for the scaffold part, they didn't assume any similarity assumptions.
Yeah, thank you. And then the second like minor point. So for instance, for your algorithm for Fed page, you require to communicate from master like 3 vectors rather than 2 comparing to scaffold, right? So is it fair to compare those 2 in communication rounds while like your algorithm requires slightly more communications in each round?
So
because if I'm not mistaken, then scaffold communicates the local iterate and the state, while you have to communicate local iterate, then the one before, and also this this state GR.
So right? You are asking the local computations, right? The
no,
local computation.
Communication. So communication from server to clients. So for Fed page, you require 3 vectors to be communicated. That's this XR, XR minus 1, and GR minus 1. While scaffold requires only to communicate XR plus state.
Oh, I know your point. Yeah, this is a small problem, but yeah, during our experiments, we actually find that even if we change the number of clients to communicate by a small constant, for example, 2 or 3, actually the curve does not change very much. Yeah. So I think that if we really need to, oh yes, this is also another point, right? So this is the case when the master delivers the message to the clients. And actually, I think in federated learning, we do not care so much about this communication because it is easy to broadcast the same thing. So broadcast is much simpler than transfer back to the master. Yes. So I think that if you consider the compression methods, actually when the server broadcast the global model, it's never compress the global model, and they only compress it after computing the gradient, right? They only compress it after transfer the message back to the server. So I think that, yeah, this is not, it should be fast. Yes, it should be fast.
Okay, so then one last question with respect to your experiments. Because you use non-federated data set, what kind of split you're using? Is it a uniform split, or you do some kind of a bias selection for clients?
Oh, you mean the non-ID setting, right? So
yeah, exactly.
So actually, yes, because so actually we just use the data set and then select them from 1 to 10, 10 to 20, 20 to 30. But actually, when the number of clients is very, very large, for example, 300 to 1,050, and each client only holds 10 data, then actually we cannot, although they are, we do not deliberately sorting the samples or the data, we cannot view them as the ID case because the number of data on a single client is not large enough, and even the variance make it very different. So I think maybe in this case, when the number of clients is very much, is very less, and the number of data on a single client is very, very much, this may consider the ID case. But for this part, for this experiment, it cannot be considered the ID case because the variance is so large. Yeah.
I can think more like you can see that always like as an IID case, but you like when you have too few samples, you don't like you assumes that those samples come from the same distribution. You don't assume you have the same sample, but if they come from the same distribution, that is not biased, then you can kind of still say that it's IID, but that has some implication for sure.
Yeah, maybe, but yes, I think that there's another question.
Yeah, so I'll try to unmute.
Do you have any intuition applying page learning framework to scaffold? Comparing fat page and scaffold with sampling queue and choosing how to how to estimate gradient. So to my understanding, this question asked if we can adding the probability to communicate with all of the clients. Is that right?
Yes, that's right.
Yeah, and
adding probability to scaffold, such like that.
Yeah, basically, I think that there is no improvements for scaffold because so for scaffold, its original algorithm or without the local steps, it is the Saga algorithm, and Saga does not communicate with all of the clients with some probability. And there's also SVRG algorithm, and SVRG may communicate with all of the clients with some probability, or communicates with all of the clients after some iterations. But the Saga convergence rate and the SVRG convergence rate remains nearly the same. In the non-convex setting, they are all n to the 2/3. And I think in the convex setting, they are all maybe epsilon, n over epsilon or something like that. So adding the probability to communicate with all of the clients, I personally think that cannot improve the scaffold. Yes.
Oh, okay. Okay, thank you.
So it seems that we are a bit over time, so maybe we can take one quick last question. Maybe there is none. So thank you again, Haoyu, for your excellent talk. It was a pleasure to host you.